The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good afternoon, everyone. I'm Chetana Rao, and it's truly my pleasure to be here this afternoon to make this presentation on the use of internally cured concrete for an intermodal facility in Dallas, Texas. And I'm with Rao Research. We are a small research company out of Champaign, Illinois. We work out of the research park at the University of Illinois incubator facility. And we've been in operation for about 2 years, and we primarily work on research projects in the area of transportation facilities. We work on projects that aim to, that essentially improve the processes and products that are used in a highway infrastructure, and processes and products that would extend the life of our highway infrastructure. I'd like to acknowledge my co-author on this, Mike Darder. He needs little introduction for anyone who knows, who works in the area of concrete pavements. Truly a legend in the field. He's the principal engineer at ARA, also in Champaign, Illinois. And truly one of the high points of my career was to work with Mike for about 12 years before I started with Rao Research. So this project was done in 2013. We were approached by the ESCSI, the Expanded Shale, Clay, and Slate Institute, that is the industry organization for lightweight aggregates. And they had used internally cured concrete on a few pavement projects that had all been showing really good performance. And they approached Mike, in fact, at ARA to do a little bit of a research project on this and get down to the details and pinpoint certain reasons or the causes for this good performance that they were noticing, and to essentially find out if there was anything they had to be a little more concerned about or mindful about for going into wider implementation efforts for the use of internally cured concrete for pavements. And I served as a consultant to ARA on this project. And the work I'm presenting here today is just a subset. It's borrowed from this larger research body of research that was done in 2013. And here's a few individuals I'd like to acknowledge. John Rees, who is with the ESCSI, and Victor Villarreal, who was formerly with TXI and now with US Concrete, I believe. I got that out of his LinkedIn profile. And there's a reference here that I cite. It was an article in Concrete International in February 2007. Victor's the author on this publication, and there was a lot of good information on this intermodal facility, the mix design itself, and some lab test data that we used in our analysis in this project. So here's a brief outline for my presentation today. I will introduce this intermodal facility in Dallas, Texas, and discuss some of the field observations that were made during a field visit and when we walked the pavement and drove the pavement in 2013. Then I'll touch upon just the concepts of internal curing and what sort of an impact internal curing has on the mechanical properties and durability of concrete. And finally, I will conclude with some theoretical analysis or the use of a mechanistic empirical analysis procedure to model the performance of internally cured concrete pavement at this intermodal facility. So here are some nice pictures and some facts and figures on this intermodal facility here. So this is the Union Pacific Intermodal Facility just south of Dallas area. It's in Hutchins, Texas, about 12 miles south of Dallas. And thank you, Google. We get all these wonderful satellite images. This facility is a 360-acre facility just west of I-45, south of Dallas. Some facts from the Union Pacific Railroad facility authorities. It has a 365,000 lift capacity, 4,000 parking stalls, 10-lane automated gate system entrance. It has, again, like the previous presenters were talking, it has 24-hour, 7-day-a-week operations, 4 loading tracks. They have plans for future expansion, and all the paving was done in 2005, and construction was performed throughout the year. Now, all these facts, again, allude to the fact that the facility basically sees heavy traffic. They are interested in keeping the efficiency high and improving the minimizing the congestion at the gate. And it's a pretty large facility, and there's basically trucks coming in and going out all the time. For every minute that we were there, this is essentially what we saw. Here's another picture of this, again shooting closer. This is the picture of the gate area with all the with the 10 lanes, and literally every truck coming in is passing through this pavement area. And this is the turning facility. This is the turning lane. They arrive into the facility along these lanes, and then they make their way into the different parts of the intermodal facility. And this area happens to be the zone for maximum traffic and maximum truck repetitions. These are some pictures from our field visit and after. So this was technically 8 years after construction, and as we were told, the pavement was showing great performance. The pavement pretty much looked pristine. It was in great shape. We could hardly find any distresses. We walked the pavement to some extent, and then we were pretty much doing windshield surveys, and the pavement slabs were in great shape. Except we saw 2 locations with some spalling at the joints, and we saw 1 crack. Now that's phenomenal. That's hardly any failures, hardly any distress development over a span of 8 years. And what is it about this pavement? It happens to be an internally cured concrete mix that was used for placing the slabs. And we have a slightly close-up shot of the slab itself. You can see some lightweight aggregate particles, and here's a small chip that we got from that small area. You can see some small lightweight aggregate particles in the intermediate size range. So having gone over the, just having given this brief introduction to the facility, we'll move over to what internal curing is all about in concrete mix design. Internal curing is essentially the use of pre-wet lightweight aggregate particles as a partial replacement to the coarse aggregate or the fine aggregate, or a combination of both. So what you're doing is essentially replacing a portion of the normal weight aggregates with pre-wet, lightweight aggregate particles. You could either, and so a couple of examples, you could replace 30% of the sand, of normal weight sand, with pre-wet, lightweight fines. Or you could replace, say, 500 pounds of coarse and fine aggregates combined with 300 pounds of intermediate lightweight aggregates. Now, what does the introduction of pre-wet lightweight aggregates do? You are incorporating moisture into the entire system. So the moisture is eventually released during the hydration process, and internal curing is therefore able to address the time-dependent moisture needs of hydrating concrete. Now, it's by no means a replacement to traditional curing, but it certainly helps with initial hydration. And from what researchers who have worked in this area for several years, almost all of their careers, say that you're taking off the chemical shrinkage. That's off the table because you've supplied enough moisture during the initial hydration, and you're significantly controlling shrinkage. And how is that different from conventional curing? When you do conventional curing, you're supplying or you're controlling the loss of moisture only from the top surface, but internal curing is actually providing moisture for the entire mass. And you're able to derive durability benefits by providing this extra moisture during the initial hydration. Your hydration process is quite efficient, and you're able to, in many ways, you're getting a much denser mix. So you're reducing permeability and all other sorts of future durability problems. So here's an example of an internally cured concrete mix design, and this is specifically the mix design that was used at the Intermodal facility. And we got this data from Victor's paper. There's the control mix and the ICC. So you have the same amount of cement, same amount of fly ash. This is the control mix. You have 1840 pounds of coarse aggregate in the control mix, and you've taken off 300 pounds for the internal concrete, for the ICC mix. Now, you've introduced intermediate lightweight aggregates. You've introduced 300 pounds here. And fine aggregates, you've again reduced it by about 200 pounds. So what you've essentially done in this mix design, compared to this conventional mix design, you have taken off about 500 pounds and added 300 pounds of lightweight aggregate. But remember, you're replacing equal volume. So you're taking off a higher weight of aggregate. Everything else remains the same amount of water. You're able to, and in this case, they were able to meet the specification requirements, 3 to 6% air, 3 to 6% air, and then there's, and the compressive strength was 4,500 psi target strength. So what is internal curing doing to the, and what kind of an impact does it have on the concrete properties? You've started with introducing more moisture during hydration, so you have a steady and prolonged moisture supply from the lightweight aggregates. And what's that doing? You're improving the hydration products. You're getting durability benefits, definitely getting lower early shrinkage, and all the other, you're also reducing all the other stresses from the restraints that would have otherwise been introduced had the concrete been shrinking. And what about mechanical properties? Now, this is a summary, sort of an average observation from several studies that we reviewed, on an average, of course, you're reducing the unit weight, on an average about 6 pounds per square foot, a cubic foot, but you're also reducing the elastic modulus by about 5%. You're lowering the coefficient of thermal expansion by about 5%, and you're improving compressive strength anywhere from 5 to 20% is what we have seen. That's the range in the data that we've reviewed in various references. Now, all these look like minor changes to the physical properties, but all of them in combination can have a far more favorable impact than the favorable impact from one of these variables being, one of these physical properties being changed. So it's really the combination of all these changes that is making the bigger difference. And what else is going on with the reduced shrinkage in terms of performance? What starts off as being reduced early age autogenous shrinkage, that magnifies over time. There's certain permanent, there's some sort of a permanent influence of early age shrinkage in concrete slabs, just like what was covered in the previous presentation today. Reducing shrinkage at early age is going to effectively reduce your permanent upward slab curling that is going to be locked in that pavement for the rest of its service life. And it's lowering your zero stress temperature, which again gives rise to a host of performance benefits. You're reducing shrinkage cracks. If it's a CRCP, a continuously reinforced concrete pavement, the design philosophy of which is all about controlling shrinkage cracks, the development of shrinkage cracks, and the failure of those shrinkage cracks, it's immensely helping a CRCP because you've controlled shrinkage right in the beginning. And it also affects your transverse crack development in the pavement. So what is the impact of temperature and moisture-related slab curling? We all know that with higher with a temperature differential or a shrinkage differential, slabs curl upwards or downwards depending on the direction of the gradient. Now, when a slab is placed on the day it is finished, and it's finished flat, there is a certain temperature gradient in the slab. So it is finished flat under that temperature gradient or under those temperature conditions. So if you were to revert the temperature gradient to this hypothetical zero gradient position, if you started off with a higher gradient, higher temperature on the top of the slab relative to the bottom, if you were to revert that temperature gradient and completely eliminate the temperature gradient, your slab is essentially locked in with a built-in, upward curling. Now, in addition to that, there is concrete shrinkage in the early age and over its life, plastic shrinkage and shrinkage further in its during the design life of the slab. What's happening is these shrinkage gradients are compounded over this existing built-in temperature gradient. So if you have higher shrinkage, you're going to see higher upward curling in the slab. That is, again, we're talking of the permanent component that stays in the slab. In addition to that, because of daily temperature gradients and seasonal moisture gradients, you're going to see the slab curling change, either increase or decrease depending on the temperature and shrinkage gradients, the daily and the seasonal temperature gradients. But this is the permanent component that stays in the pavement. Now, if you were to use something like internal curing, where you had some form of shrinkage control right at the beginning, you're dramatically reducing that upward curl. And that's really what internal curing is doing to concrete slabs. We, at this point, we haven't collected enough field data to really quantify this. There was no way, unless you went in right at the time of construction and you collected some sort of field data to quantify these parameters. But at the time that we were going in to evaluate these pavements, even though we know you're getting this benefit, there was really no way of quantifying it in your analysis. So what does upward curling do? That can be pretty detrimental for a pavement. This is, of course, not the intermodal facility, but if you had excessive upward curling or excessive shrinkage gradients in the slab, it will result in top-down cracks. Here are some pictures of some extensive failures on highway pavements. Now that's a picture that Mike used to have from the study he did on I-80 Pennsylvania. You have a core at the location of a transverse crack. You see that the crack was initiated at the top of the pavement. These were 20-foot joint spacings, 13-inch slabs, which started failing 5 years after construction because the trafficking obviously exasperates the stress development and increases damage to cause failures. Here's another picture that shows the development of top-down cracking, both from the top, both in the longitudinal and the transverse direction. So this curling can occurs in both in both directions, and you can have failures both in the longitudinal and transverse directions. These are some pictures of plastic shrinkage cracks. These appear shortly after construction, and a lot of times contractors have to go in and replace slabs before the pavement has even been open to traffic. So these are the type of failures you have a good potential to control with the use of internal curing. So coming back to internal curing and the impact it has on concrete performance, like I said, it is the combination of all these different impacts it has. It's the reduced CTE, the reduced unit weight, the higher strength, reduced modulus, and reduced built-in stresses that all in combination provide a far greater benefit to the overall performance of this kind of a pavement. And internal curing has also been considered very useful for mixes that use fly ash, because fly ash particles are kicking in after cement particles in the hydration process. Okay, so yes, empirical performance observations are great, but can we back that up with analytical modeling? Is there a reason why we're seeing good performance with internal curing? Can we explain that in a theoretical sense? So that was the whole purpose of this exercise. We used the AASHTO ME design and analysis tool that's been in practice, that's being used by several states. It's become the standard for pavement design, for performance-based pavement design, really. And I don't really have too many slides to discuss ME design because anyone in this field knows about AASHTO pavement ME design now. But it's essentially a tool that allows you to factor in the various parameters that affect pavement performance, and you're modeling the damage accumulated in the pavement from the start of its from its construction stage all the way into future. And you could use an analysis period of 20 years, 25, 30, however long, and this tool uses mechanistic concepts to calculate stresses, strains, and so on, but it also uses distress models that were calibrated using field data from sections all over the nation. So you have a very sound and a validated model to predict performance over time. So we did the ME pavement analysis. We need all inputs for this. We need climate, we need traffic, we need materials, pavement structure, and so on. We had a fairly good estimate of the amount of traffic that these pavement slabs are seeing. We know what, and we saw all Class 9 trucks. These are single trailer trucks. We used same highway loading, container loadings, and we used traffic growth of about 2%, which is very nominal. We know what the pavement structure was. It was an 8.5-inch jointed concrete pavement, 15 feet long, 12 feet wide, with dowels, and it had a 12-inch untreated aggregate base, and the subgrade was an A76, an ASHTO's A76 class soil. We know that the construction spanned through all seasons of the year, and we used an analysis period of 60 years. Something we measured on the field was this upward curling, practically zero, but we really had no way to factor that into the analysis. So here are the inputs, just a few differences between the inputs used for the control and the internal cured. Small change in unit weight, small reduction in CTE, increase in strength, and in this case it was practically, very similar E values. Everything else was, either computed by the program or we had lab data for this. So when we modeled this pavement, we're showing you the control and the ICC sections here. On the x-axis is plotted the age, and on the y-axis you have the development of slab cracking. So over a 60-year analysis period, you're seeing that in the control section, you're going to get about 15% cracking at the end of 60 years, but you're getting just about 8% cracking in the ICC, in the internal cured concrete. And usually the cutoff, the criterion is about 10% for slab cracking. So that's a theoretical verification for the observed performance on the pavement. And of course, what we see on the pavement today matches closely with what we're predicting here, but this is also at a 90% reliability. So a small change to each of those mechanical properties has resulted in a large benefit in terms of performance. And here's performance in terms of faulting and IRI. They're both within the typically used criteria. So there's a few other field projects that we examined under this project. This is the State Highway 121, a CRCP project in Dallas, and a few residential streets. We did similar analysis for all these projects, and we were able to account for the benefit of using internal cured concrete, or we were able to model that. And with this, we come to the conclusion. In conclusion slide, and what we're trying to learn from here is that introducing pre-wet lightweight aggregates is definitely making some favorable changes to the concrete properties, and any analysis, mechanistic empirical analysis, validates this excellent performance, and ICC can be used in heavy-duty pavement applications.
Thank you. Any questions?
Thank you. I drive by the Hutchins facility all the time, so it's hard to miss. I'm just curious, have you done any relative humidity testing, in situ relative humidity testing of the pavement that you did versus the control pavements on site?
No, we have not done that, and there were no control sections.
So they didn't, but they had a control mix design, I thought.
Design,
okay,
yes.
But that was just...
When they were batching and trial batching, making the mixes, they had these.
So the whole site has the lightweight aggregate. Okay. Well, that would be interesting to do, and then model that back to the curling profiles, as you said. If you're looking for data, that would be the best way to look at that, because I've seen the same thing in the Dallas-Fort Worth Metroplex on industrial floors. It's that differential RH top to bottom that affects how much these floor slabs curl.
Yeah. Thank you.
Thank you very much.